All right, this is the third video in the forces section. This video is on tension and normal reaction. In a separate video, I'm going to do the second part of section 3 on friction, but we're just covering tension and normal reaction here. So tension, what is it? It's a force along a connected medium, such as a rope or a string or a rod, maybe. So if we've got, let's say, a box on a surface, maybe a carpet here, and I'm pulling on a space connected to a string, and I'm pulling on the string, then the force is applied to the box through the string, and that force is a tension in the string. So if we're modeling this situation, we'd probably draw it something like this and show that force. Okay, so now the other interesting thing here is that tension in a string or rope will act in both directions at the same time. So if we look at this example here, the two fellas in a bit of a tug of war here. Okay, so they're pulling in opposite directions. So in actual fact, there's a force pulling this guy on the left, pulling him to the right, and there's a force pulling the right-hand guy to the left. So that's the interesting thing with tension, is it applies in a string in or rope in both directions at the same time. Okay, so and now the thing is that if the string or rope is termed light and inextensible, and that's a term that you'll see quite a lot in these problems. In fact, they're always light and inextensible. Then those forces will be equal. So the force that is being applied to this left-hand guy to pull him that way is that arrow there, and the one pulling this guy to the left is this arrow here, and those forces are going to be equal. Now, it doesn't mean to say that that the tug of war will be a draw and they'll go on forever. I mean, this guy and it depends what their pulling power is. That just represents the tension in the string. But if this guy is pulling with, say, 1,000 newtons, and this one with 900 newtons, I mean, this one, the guy on the right, looks as if he means business a bit more, doesn't he? So the net force on this guy is going to be, well, 100. He's going to be, well, he's 1,000 minus t newtons to the right, and this one's going to be 900 minus t to the left. So the guy on the right is going to win, isn't he? So just as a bit of extra, not something that we're really considering at this stage, but you might just ask yourself, what is the value of t? Do we know what the value of t is from this? Well, not as such, but if both of these guys were the same mass, then they're both, when they start moving, they're both going to move with the same acceleration. So we'll find that actually that the tension is equal to halfway value between these two, 950. If they're different masses, then we've got some calculation to do. Anyway, hold that thought, because you know, that's basically a later section. But this is a sort of model that we're going to be faced with quite often with problems with tensioning. Right, okay, let's have a look at an example which involves tension. Two particles are held in equilibrium on a smooth, that means to say there's no friction, inclined planes connected by a light inextensible string, as ever, across a light frictionless pulley, and at A level they're pretty well always light and frictionless. So the first question is, find the tension in the string. Now, this question involves what's called a system of particles. A system, we only need two to make it a system. We've got the 3 kilogram one and an m kilogram one. We don't know the value of m yet. So this makes it a system of particles. And the key thing here is that we need to note is that there is a tension in this string. It is effectively acting upwards for the m kilogram and upwards again for the 3 kilogram. And those tensions are equal. So we can use other features of this particular model in order to work out what T is. So let's just to work out what M is in particular. Let's just have a look at that. So if we just look at this this 3 kilogram particle, for instance, we're gonna call the tension T. That will be the value T newtons. And first of all, we consider this 3 kilogram particle. Okay, well, what have we got? Well, we've got the tension pulling it up the slope. We've got the weight, which actually is not acting down the slope. It's not acting perpendicular to the slope. It's acting vertically. But we are interested in the component along the plane. So we're going to have to resolve this 3g, that's the force that arises from a mass of 3 kilograms. So that is 3g. And we're going to have to resolve it. Well, we resolve it into perpendicular directions. We're not actually interested in this one. There's no motion perpendicular to the plane, so it doesn't actually serve us to do that for this part of the question. But if we look and resolve it down the plane, then basically we're going to get 3g sine 60. This one is 3g cos 60 if we were interested in it. And this one is 3g sine 60. And just a little aside around here is that we multiply the original one by the angle. So that would make this perpendicular one 3g cos 60. And this one here would therefore be 3g sine cos 30, 3g cos 30. But cos 30 is the same as sine 60. And it really, it is kind of more convenient, probably easy to remember as well, if we just think of that as sine 60. So this is 3g cos 60, this is 3g sine 60. Okay, so we got that, 3g sine 60. And of course, this is an equilibrium problem, so that the forces must net out to 0. So therefore, T is going to be equal to 3g sine 60. And that's going to work out as a value of T as 3 root 3 over 2 g newtons. That's applying what we know about the values of sine 60. Okay, so we've got tension. Now, when we look at the other side of the problem, now we don't know M, but having done the first part of the problem, we do know T. So that is the tension that's acting up the plane. So if we consider this m kilogram particle, the weight resolved along the plane is mg sine 30. We're dealing with 30 degrees this time, so mg sine 30. And the tension upwards is this value we just calculated. So we've got our equation there, mg sine 30 equals 3 root 3 over 2g. And if we just work that through, we're going to find that m is equal to 3 root 3 kilograms. Okay, so in this model, this mass here is greater than the one on there, which I think intuitively is what you would expect. Okay, so that is a question on tension. And there are other worked examples on tension to help to illustrate that, but we'll think about normal reaction now. So we've got a particle, 10 kilograms, sitting on a table. So it experiences a downward force of 10 G newtons. That's due to its own mass under gravity. So there's a force acting on this, which is its own weight. But this doesn't accelerate downwards, does it? If we're thinking about Newton, F equals ma, force equals mass times acceleration. It's not accelerating. It's not accelerating because it's on the table. And in actual fact, there is an equal opposing force exerted by the table on the particle. So this is the situation that we've actually got, is we've actually got the force downwards, which is its weight, and we've got the normal reaction, and these two must net out to 0. They must be equal and opposing, because the particle is not moving. And the normal reaction is, well, normal basically means perpendicular, and so that is that force always acts perpendicularly to the surface. All right, so if we have a look at a kind of problem on normal reaction, just to help consolidate that thinking, we've got a pile of 4 uniform blocks in equilibrium on a horizontal table. Their masses are shown: 4 kilograms, 5 kilograms, 7 and 10. Here we go. Mark on the diagram the magnitude and direction of each of the forces acting on the 7 kilogram block. Right, well, we've got obviously sitting on top of the 7 kilogram, we've got 4 and 5. So there's so these are exerting a downward force of 9 G newtons down onto the 7 kilogram block. The 7 kilogram block itself is, of course, is subject to a force due to its own mass, i.e. its weight, and that is 7 kilograms. So there is a total of, if we're thinking about this surface here between the 7 and the 10, then there is a total of 16 G acting downwards. Again, it's in equilibrium, so there must be a force of 16 G acting upwards from this surface here onto the 7 kilogram block. So that balances it out. So we've got total of 16 downwards, and therefore a total of 16 upwards. So that is the idea of normal reaction. Okay, so we're going to just have a look at one more example, which looks at both, well, basically looking at normal reaction. The crate is held on a smooth 30-degree plane by a force of P newtons, as shown. What is the value of P? So we've got this thing sitting on here. It's got its weight, 10 G, and then it's got this thing coming in obliquely. Well, it's coming in a sort of angle of 30 degrees to the top, isn't it? So this P is inclined at 30 degrees to the plane. All right, so we've kind of recreated that here, but also added in the forces. So we've got, again, we're not interested in this part A with perpendicular to the plane. We're just looking at along the plane. And what we've got is when we resolve along the plane, this weight, the components of the weight along the plane is 10 G sine 30. Okay. Okay, this angle here being 60 degrees, cos 60 equals sine 30. Okay, so that's 10 G sine 30. And then going up the plane, well, we've got this, but resolved through this angle. All right, this angle being 30. So this going up the plane is P cos 30. So now those are the only two forces acting on there. So what we've got is that this P cos 30 is going to be equal to 10g sine 30 in that equation there. Now basically we just got an equation in P which you can work through like this, and that's going to give us 10 root 3 g newtons. Substitute whatever value of g you need if you need a numeric solution, 9.8 or 10 or whatever. So that has evaluated P for us. Now, the second part is, what is the normal reaction of the surface of the slope on the crate? Now we've got, so we just kind of brought that out in this diagram here. How we can forget that bit. Three forces act perpendicular to the plane. So we've got the, when we're looking perpendicular to the plane, we've got the weight resolved perpendicularly, in other words, through 30 degrees, this angle here, so that's 10g cos 30. We've got this force P resolved perpendicularly, so that's through that angle. Okay, so it would be cos 60, but we've called it P sine 30. Okay, and then we've got the normal reaction as well. So now these are the only three forces that are acting perpendicular to the plane. And we can see from the arrows that this is going to equal that plus that. So N equals P sine 30 plus 10g cos 30. Okay. And again, we know what P is because we calculated it up here, so we can substitute that in. So that's going to give us this. You can just kind of pause and satisfy yourself of that if you wish, but take it from me, that evaluates to 10 root 3 g newtons. And again, if you need to put a numerical value in there, then you can substitute your 9.8 or 9.81, whatever, into there. So that is basically the normal reaction. Now, why we need normal reaction is usually because we want to find friction. Now, this is a smooth plane, so whatever the normal reaction is, then the friction is going to be 0. But if we have a rough plane, that's going to give rise to a force of friction, which we're going to talk about in the next video. So that's it. It's a kind of a normal reaction. It's a little about the effective weight of it. I always think, the effective weight here is going to be, it's like if you're stood on the floor, you're 80 kilograms, like me, and that's the force that you're pushing down on the floor. If then somebody hands you a 10-kilogram weight, and then you're pushing down with 90 kilograms. So that's the idea of normal reaction. Anyway, we're going to expand on that a little bit more when we talk about friction in the next video. So thanks for listening.